Right, so this is a question called using an inductor to produce a spark. So in the circuit below, for a spark to be produced between the gap AB, the voltage across AB must be greater than 1.20 times 10 to the 2 volts, or 120 volts. Switch 1 is closed, and the current in the circuit rises to a constant value of 1.7 amps. Calculate the energy stored in the inductor when the current has risen to the maximum value. Okay, what are we given here? We're given an inductance here. And it looks like the inductor also has some of its own resistance here, so it's a real inductor. This is the maximum current, and we want the energy stored. So energy is equal to 1/2 Li squared for an inductor. And so in this case, it's just a straightforward substitution. 1/2 times 0.510 times I squared, which is 1.70 squared, which gives us a value of, whoops, where's my calculator? There we go. So 1/2 times 0.510 times 1.7 squared equals 0.73695. Let's get rid of this thing here. And the value again was 0.73695. And that's in joules. And we want it to 3 significant figures, so that's 0.737 joules. Okay. Calculate the value of R shown on the diagram and explain its effect on the maximum current. So the maximum current, so I max, that'll be the steady current that we've reached once the inductor is not doing anything anymore. So I max is going to be, it's going to be equal to V over R, which is, so therefore R is equal to V over I max, which is equal to 120 over 1.7, which is 70.588 or 70.6 ohms. And this resistance limits the maximum current as I max is equal to V over R. I think that's pretty much all we can say about that resistance. Explain the effect of inductance on the time it takes for the current to rise to its maximum value. Okay, so we can say the inductance affects the time constant. As tau is equal to L over R. So the greater the inductance, the greater the time taken for current to increase to 63% of max. The current will effectively reach maximum after 5 time constants. So this will take a longer time if L is greater. Okay, have we answered the question fully? Explain the effect of inductance on the time it takes for the current to rise to its maximum value. I think we've done that. Okay, next question. Switch 2 is closed in addition to switch 1. Explain what happens to the voltage across the inductor. Okay, let's have a look at this circuit. So we've closed switch 1 here. And we're now closing switch 2 as well. But there's a gap here in the circuit. So switch 2 is just going to introduce a circuit that's not closed. So that's not going to do anything. That's a strange question, but so be it. I guess we need to recognize that actually closing that switch isn't going to do anything. So nothing happens to the voltage across the inductor because the bottom branch has a gap. And no current will flow there. In this branch. Thus, as there is no change in current through the inductor, there will be no voltage induced. Okay. Switch 1 is opened, leaving switch 2 closed. Explain why a spark could be produced across the gap. Let's have a look here. So there's a current flowing through this branch, and we suddenly open this switch. That means that the current will suddenly stop, so we'll get a very quick decrease in the current, which means that we will have a very large voltage across the inductor, which means that we might be able to produce a voltage large enough to create a spark across that gap. Okay, let's have a look and see. Oops, I'm doing something weird here. Let's try that again. All right, so when switch 1 is open. So the key things that we want to say here is when switch 1 is opened, we've basically an open switch is like a very, very large resistance. And so the current will suddenly stop, which means that the induced voltage across the inductor will be very large because delta I over delta T is very big. And we need a large voltage to create a spark across the gap. Okay, so let's get each of those points really clear. So when switch 1 is opened, the current suddenly drops as resistance suddenly becomes huge. Maybe we'll talk about the time constant. That'll give us a sense of how quickly the current is dropping. With the open switch, which is huge resistance, the time constant becomes very small as tau is equal to L over R. Thus, the current drops very quickly. Induced voltage across inductor is given by V equals delta I, also negative L delta I over delta T. So as delta I is large and delta T is tiny, the induced voltage will be huge, potentially large enough to produce a spark. Okay, explain why a spark could be produced. So we open switch 1, the current suddenly dropped, which basically an open switch, because you now introduced a gap of air in that circuit, the resistance becomes huge. With the open switch's huge resistance, the time constant becomes very small, because R here is big. Thus the current will drop very quickly. The induced voltage across the inductor is given by negative L times the rate of change of current. So because delta I is quite big and delta T is really, really small, the induced voltage will be huge, and that might be large enough to produce a spark across the gap. Cool. So I feel like we fully answered that question.